There we go. Okay. Alrighty. How's everybody doing today? Did you say good night or good day? Oh no, my thing wasn't working. I don't know why. All right. Do. All right. So, just FYI, I am live streaming to YouTube at the moment. So, if you guys don't like how it is on Google Meet, you can watch it on YouTube Live. All right. So, Afonso's here. Alvaro is not. Andrew is here. Anthony is not. Cameron is not. Caesar is not. Jamar, nope. Cameron is here. Okay, Denasia is here. Destiny's here. Elijah. Kaylee. Kimberly. Liza. Monte. Myra. Michael is not. Miguel. Naheem. Sayas. Anisha. Jana. Sean's here. Michael's here. Shanice and Trinity. Alright, Caesar. Nope. It's alright, I got you, Michael. Jamar's not. Kaylee. Renchana and Trinity. Okay. Yeah, I got you. Elijah, did you finish the assignments? Elijah, did you get the assignments done? Okay, cool. I'll put them in the grade book, hopefully by tonight. Alrighty. So, let me move this over here. Okay. Refresh this. All right. Reset. Cool. All right. So, on Monday, we talked about the basics of forces. For those of you who weren't here, we this full screen. All right. So what we did was we talked about forces and how forces interact with each other. So if I have one little dude acting on this cart, like he's pulling the cart with a force of 50 newtons, the sum of the forces, because there's only one, is 50 newtons. So in this situation, this is an unbalanced situation or scenario. Okay, I've been using situation and scenario a lot today. Sorry. So the sum of all the forces acting on the cart right here, since there's only one, it's going to be 50. And if there is a value for the sum of all the forces, if it's something other than 0, then the object is going to change its state of motion. This is an unbalanced scenario. Therefore, it's going to start to accelerate. Okay. So it's initially at rest, and then it's going to start to move. So to prove that it's actually accelerating and not moving at a constant speed, as time goes on, you'll see the needle start to go around an increase in speed. So when I hit go, it starts to increase because this is unbalanced. Okay. Now, in order to balance it out, there has to be an equal but opposite force acting at the same time. And if I've got negative 50 or 50 going to the left and I've got 50 going to the right, negative 50 plus 50, the sum of those forces will equal 0. So this is going to act as if there are no forces acting on the object at all, because the force of this guy is getting canceled out by this guy. So when I hit go, we can expect it not to move. And it's not moving. So what I also want to illustrate is that this dude is pulling with 100 newtons, and each one of these guys is pulling with 50 newtons. So I've got negative 50, and then a positive 100. So overall, I've got a negative 100, but that's getting canceled out by the positive 100. So this is the same scenario as before. If I add these up, the negative 100 and the positive 100, I get 0. So when I hit go, nothing happens. Cool. So the sum of the forces, or the net force, if it is 0, the object will not move, or it won't change its state of motion. I can flip that around. If the object is not changing its state of motion, we can conclude that the sum of the forces must be equal to 0, which then leads us to saying that the forces, if there's only 2, or the forces in one direction, must be equal in value. So negative, the value is 100, but they're in opposite directions. Does that make sense? If I notice that the object is not changing its state of motion in a certain axis, I know that all the forces in that axis must be canceling out somehow. Cool. So what we did last time was, if I go back over here, we had some examples. Okay, so what we did was we applied a force of 50 newtons to a mass of 50 kilograms, and we wanted to figure out what the acceleration value was. So if I'm going to pause it, I'm going to put 50 newtons. So I'm applying 50 newtons to this object. I keep looking at the chat over here. I apologize. Look at the camera. So if I apply 50 newtons to a mass of 50 kilograms, I'm going to have an acceleration. And the reason, like how I can prove that, is as time progresses, the value right here is going to increase as time goes on. So when I hit play, hopefully we'd all agree that this is increasing in value. Now, if I increase the amount of mass that I'm pushing, so if I double the mass, so if I put 2 boxes, both equaling 50 kilograms, what should happen to how much I'm accelerating? So if I'm going to be pushing something that's heavier, it's not going to speed up as quickly, right? It's going to be more difficult. Yeah. So that's what we discussed on the second scenario. So going from example A down to example B, what we did was, sorry, I'm going to pull this over. We took the mass and we multiplied it by 2. So we doubled the mass. So that means that my acceleration has to be cut in half to still equal 50. Okay, so you can think about it abstractly like that, but if that's confusing, in order to figure out what acceleration is, I need to get acceleration by itself. So I've got 100 times A. In order to get rid of that 100 and get A by itself, I just divide by 100. It cancels out on the right side, and I get 50 over 100. That reduces to 1/2. So from example A to example B, my acceleration decreased in value. So that means that I'm not going to be speeding up as quickly. Is everybody tracking so far? And then lastly, what we talked about was, So notice how this is not climbing up nearly as quickly as when I take off the mass. Put the mass back on. It slows down. Cool. So let me reset this. Come to 0. Okay. All right, so if I apply 50 newtons, like that, and then, oh, hold on. This was a scenario. I apologize. Pause. All right, so this was situation B. I have 100 kilograms. I'm applying 50 newtons. And scenario C, what I changed was I still had the 100 kilograms, but I now increased my force by a factor of 5. So I quintupled my force. So if I go back over here, so it's paused. So I go from 50 newtons. Let me show you guys. So watch the velocity or the speed here. It's kind of slow. But then if I increase my force by a factor of 5, it's obviously going to move quicker, right? Cool. So in order to figure out what that acceleration was, what the value of that acceleration is, I should say, I use this equation. I want to solve for A. So I divide both sides by 100. It cancels out over here. So 250 divided by 100. Whenever I'm dividing by 100, I just move to the left 2 times, and I should get 2.5. And that's what I get here. So 2.5 meters per second squared. Any questions? Just checking to make sure my attendance is up to date. Looks like I'm missing somebody. Alvaro, Anthony, Caesar, nope. Jamar. Yep, there's Jamar. All right, remember, when you guys come in late, let me know. Like, I'm not going to mark off for tardiness. I just want to make sure that I accurately have attendance done. No, you're good. Okay. So, hopefully there's no questions. Everybody's caught up so far. All right, and then what we did was we discussed the normal force. So, get rid of all that. So, when we talked about the normal force, what the normal force is when an object is making contact with a surface, okay? And it's going to be preventing the object from going into that surface, okay? So, in other words, I've got a box sitting on a surface, the green line, and if that surface wasn't there, the box would fall to the center of the earth, okay? So, if I have a box that's sitting on the ground, I know that it's not moving in the vertical axis, right? If it's just stationary at rest, I know that it's not somehow morphing into the ground and it's not somehow transcending into the heavens. So it's just at rest. So because it's at rest, just like in this situation, when I hit go, it's at rest. And because it's at rest, when I'm applying the forces, I can conclude that the sum of the forces is equal to 0. If the sum of the forces is equal to 0, I know that when the forces are acting on each other, they're going to be equal but opposite. Okay? So if I know gravity is always present when I have a mass on Earth, just like in this situation, I've got the box, it's on Earth, it has mass, gravity's always acting on it. So the red vector line, the red arrow, I should say, is pointing down, so that's always present. So the normal force I know must be present and in the opposite direction with the same magnitude, the same number as the force due to gravity or the weight. It's just pointing in the opposite direction. Cool. If I have a vertical surface, so if this is my surface like this, the normal force is going to be perpendicular to it or normal to that surface. So the definition, the reason why it's called the normal force is because the force is always perpendicular to that surface. If I had a surface that was off at an angle, the normal force will always be perpendicular. Are we tracking? If I had a plane, I would have a force perpendicular like that. So coming out of the page or into the page. It's going to be in a perpendicular axis. Any questions so far? Okay. So where we left off last time was a situation like not a demonstration, but an example of I had a box and I'm pushing the box against the wall. Okay. And we were discussing the forces acting on that box. So the first iteration of this, what I was explaining was I had the box against the wall, and then I removed my hand, so it was no longer applying a force horizontally. And at the very instant I'm no longer making contact, I took a snapshot. And I wanted to figure out what forces are acting on that box at that instant. So that scenario would look like this. So I had a box, and the instant I took my hand off, what's the only force acting on that box at the moment? I'm no longer pushing it. So force push. That means that there's no normal force. Yeah. So the only force that's present would be the force due to gravity, because that's always present. So there's no force push, there's no force normal, and the only force that's present would be the force due to gravity. And if I only have one force, this is an unbalanced scenario. And if something is unbalanced, that means that the object is going to change its state of motion. So if we think about this logically, if I push my hand against the box and I'm pushing the box against the wall, and then I remove my hand from the box, what happens to the box? It falls to the ground. Because I am no longer pushing it against the wall, I remove that force, and then it drops. So that's the situation that I've got right here. Cool. But in the event that I am pushing on the box, that's where we left off. So we always have the force due to gravity, so this is going to be there. Cool. And if I'm pushing on the box, I know that the box isn't going into the wall and it's not somehow moving away from the wall. Its horizontal position is remaining constant, so it's not changing its state of motion. So I know that the force being pushed into the box is going to be equal in magnitude to the normal force. They're going to be equal values, just like this, but they're going to be in opposite directions. So when I add them up, the sum of the forces will equal 0. Cool? The same goes for the vertical axis. I know that when I'm pushing my hand against the wall, against the box, and I'm pushing that against the wall, if I'm pushing it against the wall, I'm trying to keep it from going down, right? And it's obviously not going to go up. if I'm pushing horizontally. So in order for it to make sense, I am pushing against the wall, pushing against the box that is pushing against the wall. And I know I can observe that the box is not changing its state of motion vertically. So therefore, I know that it's balanced. So therefore, I know that the sum of the forces is equal to 0. And that means that there has to be at least two forces present, minimum, and that they are equal but opposite. So since I know the force due to gravity is always present, there must be an equal yet opposite force to counteract the force due to gravity. And in this situation, this is due to the force of friction. Okay? So the very last thing that we talked about was, would it be easier to hold the box against the wall that was lined with sandpaper, or would it be easier to hold the box against the wall that was lined with ice? Which one would be, let's say easier? Yeah, which one would be more easy? Yeah, the sandpaper. So obviously because the sandpaper has more friction, right? Okay. So if you think about it, I really wish there was a way that I wish I had I have a demonstration in my head that I think would express this perfectly. Um, but I don't know if I can verbally relate this. So what the situation is, I will have two identical boxes and they're pressed up against the wall, and there's going to be side A and side B. So side A is going to have sandpaper, side B will be an ice block. And the boxes are being pushed into the wall by some sort of I don't know, pneumatic thing, something that's applying a force. And then what the demonstration would represent, what it would do is we would lower the amount of force on both sides simultaneously, and then observe which one fell first. And in that situation, the one that's pushing up against the ice would fall first because there's less friction. Does that make sense? Okay. All right. So hopefully everybody's caught up, and it makes sense. It was a nice little review for you. Side note, I make sure that you guys complete the Ed puzzle that I posted on either Monday or Tuesday. It is due tonight at midnight. It's just a 10-minute video. It's on completion. Don't worry about getting the questions wrong. The way that they word it in the video is a little strange, but make sure that you do it, guys. I mean, you guys have had a couple days to do it. So yeah, easy 10 points. Okay. Now, what I want to talk about today is friction. So what is friction? Who can give me a definition of what friction is? Anybody? You can unmute. Might be a little bit easier. The force between two objects. Okay. When two objects make contact. Yeah. So friction is the force that's created or produced when two objects make contact. Okay. Is friction good or bad? So Cameron got it. It's both. There are some situations where we want friction, and there are other situations where we don't want friction. Like fire. Oh, you mean like the little stick and stuff like that? Yeah. So that's when we would want friction. Or like if you're holding on to something, or uh, if you're trying to pick something up, you definitely want friction because otherwise you can't pick it up. Um, but then there's other situations where we want to reduce friction, like opening a door or in an engine. Like if you don't put oil in your engine, uh, there's no lubrication, so there's going to be a lot of friction and it'll cause damage to the engine. Bearings, things that are in constant contact and sliding against each other, we want to lubricate those situations to reduce friction so that way there's no damage to the metals. So it's good and bad. Um, so when it comes to friction, there are two types. There's going to be kinetic friction and static friction. Okay, when I say static, I don't mean it like the static electricity. I mean static in the terms of stationary or not moving. Cool. So the best example that I can give for you guys, or the easiest example, is think about a situation where you had to move a large piece of furniture or a couch or a bed or something and had to slide it across the surface. Okay. Was it When was it easier to move that object? Like when did you feel like you weren't it didn't require as much force? When it was stationary or when it was moving? Like once it started to move. When was it harder to push it? Has anybody done that? Yeah. So when it's stationary, it's more difficult to start it to get to move, to get it to initially get it to move. It requires more force to like break it free from the surface. But once it starts to move, it's much easier to keep it going. It requires a lot less force to continue to make it move. Has everybody experienced that, or at least can understand what I'm saying? Okay, so that's a very good demonstration of static friction versus kinetic friction. Friction is present in both situations where it's stationary and when it's moving, but something changes where it requires less force after it begins to move. And having static friction and kinetic friction explains that. Cool? All right. So, this is going to look scary because it's already pre written. I did this for my last block, but I want to kind of break this down for you. All right. So, don't look at the screen that I'm getting ready to put up and mind blow. Okay. So, just bear with me. All right. Told you. So, let me kind of break this down. So, the force due to friction, it's going to be a capital F with a subscript of what I call a script F. Okay, so how I write that, it looks like a little weird S with an F, like with a horizontal line. Okay, so this would be the friction F. All right, so the force due to friction is going to be equal to this thing, and I'll come back to this, times the normal force. All right, so we discussed the normal force earlier in the class. So what on earth is this? So this is the Greek symbol mu. Okay. And the coefficient of friction, all it is that it describes how frictiony a surface is. And when it comes to the value of mu, it has to be greater than 0, but also less than 1. So whenever you see the coefficient of friction, whether it be coefficient of static friction or the coefficient of kinetic friction, it's always going to be like 0.12 or 0.9 or 0.59. It's going to be bigger than 0, but it's not going to be greater than or equal to 1. Cool. And I'm not going to go into detail about like how this came about, like why it is like that. In a nutshell, it's just a ratio of two different things. So there aren't any units. It's just comparing two different things. Um, and it turns out that this ratio is always going to be zero, uh, greater than zero, but less than one. Make sense? So if I gave you guys, so we'll say sandpaper, um, glass, and ice. Just real simple. We'll do 0.12, 0.86, and 0.56. All right. So the sandpaper, like, how would I rank this? If I have something that's more frictiony, would I have a higher coefficient of friction or a lower coefficient of friction? I would have higher. So with sandpaper, which number would it match up with? And I'm just pulling these numbers out of thin air. I'm trying to demonstrate. All right, so which one of these values is the highest? Well, before we even say that, which one of these is the most frictiony? The sandpaper, right? So if the sandpaper is the highest, then I need to look at these numbers and match it up with the highest number there. So which one would that be? Yeah, 0.86. Cool. And then out of glass and ice, which one is more frictiony? All right, so Michael says ice. So think about this. If I had a have y'all seen those things where you can like you can make a there's a mold, like a silicone mold that you can make glasses out of, like it's made out of ice, but you can pour drinks into it and you can like peel it out of the silicone. It's like an ice cup. You know what I'm talking about? You ever seen that before? So if you haven't, they have these little molds that you can dump water into, put it in the freezer, and it freezes the ice, and then you can peel that ice out, and it's in the form of a cup. Um, so if I had a cup that was solely made of ice and then a cup that was made out of glass, which one was easier to hold? Like, which one would you think that you could hold for 10 minutes, or we'll say 5 minutes, without dropping it, without having to hold the bottom? Yeah, the glass, right? So the glass is going to be more frictiony than the ice. So the glass would match up with this or with that. Yeah. So the 0.56. And then lastly, the ice would be like that. Cool. Is there any confusion about that? Okay. Where am I at? Okay. So when it comes to the difference between static and kinetic, mu is the symbol that we represent the coefficient of friction, how frictiony that surface is. And it's of the surface, not of the object. Okay, I want to make that clear. So mu sub s is the coefficient of static friction, and mu sub k, and I'm saying mu sub sub k, sub as in subscript, that's going to be the coefficient of kinetic friction. Cool. All right. So if I go back over here, the force due to friction is just going to be the coefficient of friction multiplied by the normal force. Okay. So if I, for example, wanted to figure out the force due to static friction and the force due to kinetic friction, how I differentiate those two is using these mu's respectively. Cool? So just like this. Mu sub s, or sorry, the force due to static friction is like, oh, here, I'll do it right below here. I had it on the other screen. So the force due to static friction is going to be mu sub s times the normal force. And then the force due to kinetic friction is going to be mu sub k times the normal force. Any questions about that? Okay. All right. So the last thing that we're going to do today is I want to go over an example. All right. Now, let's do this. So this is what I wanted to do. All right, bear with me. No, I shouldn't change the. Dang it. All right, so this is almost it. For it to stop. Okay, this should be it. Yeah, okay, cool. All right, so I apologize for that, guys. All right, what I want to demonstrate here is this what you're doing like on Canvas? What do you mean by that? Oh, is this thing right here, this simulation? Is this on Canvas or is what I'm writing on Canvas? The simulation is not on Canvas. How about I put this in the chat? Got those in the chat for you. Yep. Okay. So in this situation, I want you guys to pay attention to a couple of different things. So this demonstrates really well the difference in the effect of static versus kinetic friction. So I wish that there was a way that I could manually put in the value for the friction. That's why, like, I'm trying to make the numbers look really nice, and I think I got it where I needed it. Excuse me. So what's going to happen is I'm going to apply 200 newtons. So notice when I do this, the sum of the forces is equal to 0. I apply 50 newtons. The friction force is 50 newtons. Cool. I apply 100 newtons. Friction force is like, all right, bet, I got you. I ain't going to let this happen. I'm going to increase to 100. Okay. I increase to 115. Friction's like, not today. I'm gonna bank it up to 100 or 150. Go up to 200, nothing, right? So all the way up until 200 newtons, nothing is happening. Now, if I increase it by just one more newton, all right, so I was making jumps of 50, but if I go at any, if I increase the amount of force being applied just by like a little tiny bit, then what's going to happen is friction's going to be like, ugh, can't do this anymore. And then it's going to go switch to kinetic friction. Okay. So what I want you guys to really pay attention to is, as of right now, the forces are equal. 200 newtons, 200 newtons. If I go to 201 on the, if I push with 201 newtons, I want you guys to really pay attention to what the friction force does. Okay. Is everybody ready? If I click just one more newton on there, oh, come on. Oh, I didn't hit play. Dang it. Of course. Hit play. Dun, dun, dun. Fail. All right. So if I hit one more newton on, if I increase by one more newton, watch this number here. What happened? So I'll switch back to 0. I'll do it one more time. So I'm going to increase to 200. Yeah. So the amount of friction force when it's stationary, the maximum amount of force required or able to be produced by friction is 200 newtons, right? Now, if I go one more newton higher, I go over that threshold and it switches to kinetic friction. And kinetic friction is always going to be less than static friction. That's why it's easier to push an object or slide an object across the floor once it's already starting to move. If it's stationary, I have to apply 200 newtons, right? But if I go 1 newton higher, friction force is no longer 200, it's now 150. So it is much easier to move the object. So what I can do, I can still continue to move this object. If I drop my force down to 50, or I decrease it by 50 newtons, I'm now only applying 151 newtons, right? But it's still moving. And I can even decrease it by one more. So now I'm going to be traveling at a constant speed because the sum of the forces is equal to 0. I'm pushing with 150 and friction's pushing back with 150. But notice what I've been reiterating the entire time is that if my forces are balanced and the sum of the forces is equal to 0, the state of motion of the object will not change. Okay? So when I'm at 151 newtons, I've got 151 going to the right and I've got 150 going to the left. Overall, I've got a sum of the forces. I've got a net force of 1 newton to the right. And notice how over time this is slowly increasing in speed because I have a net force, right? But if I go back down to 150, this speed will remain the same this whole time. Okay? So what would happen if I immediately stopped applying a force? What would happen to the box? If I no longer applied this 150 newtons, if this orange one went away, what forces in the horizontal axis are still present? Yeah, friction is still present, right? Because the objects are still making contact and it's still sliding. So friction doesn't just magically disappear. It would be really cool if that could happen because, like, if I had a device that could just randomly turn off friction, you better believe that I would use that at school. kids walking down the hallway and they're not supposed to turn friction off and they fall right on their butt. Be glorious and hilarious. But I would make sure I would like throw a pillow at them first so they would land on it. So what I'm going to do, so I'm going to pause it real quick, and then I'm going to decrease my force down to 0. And then I want you guys to watch the speed once I hit play again. Okay. So now the only force that's present is the friction force. So what do you think is going to happen to the speed? If it's already currently moving to the right, force of friction is going to the left. So it's trying to accelerate it in the opposite direction of its velocity. So if I'm going this way and I'm accelerating that way, what would happen if friction did not exist? It would continue on forever. So there's a really cool episode of Magic School Bus. Like when I was growing up, I watched the Magic School Bus, and like that was my show, and I think that inspired me to get into science. But there was a really good episode where they were talking about friction, and it was really funny to watch. I can't remember the redhead kid's name, saying that he hated friction, and then Miss Frizzle turned friction off, and everybody was slipping and sliding, and they couldn't stand up, and like, because if you don't have friction, then you're gonna slip right. Like you can't make contact with the floor. Like nothing grips. There's no grip anywhere. So it was not fun at all. It was funny when I was a kid. So back to this. When I hit play, what do you guys predict is going to happen with the box? If it's already currently going to the right, but friction is going to the left, so I'm already moving. So if I didn't have any forces at all, so if my net force is 0, it's going to continue on, right? But if I remove the applied force, do I have a net force acting on the box as of right now? Is the sum of the forces equal to 0? Sum of the forces equal to 0 when I'm applying the force, because I've got two forces, they're both equal to 150. But if I'm not pushing on it, I take my force away. There's only two forces initially. I take mine away. There's only one force. And it's impossible to have sum of the forces equal to 0 if you just have one force. Make sense? If I have one force, it can't get canceled out by anything. So if I just have friction being applied, I have a force of whatever friction is in the opposite direction of the motion. Make sense? So if I'm moving to the right, and think about this in a real world sense. If I had a hockey puck and I slid it across the cafeteria floor, would it just continue on forever? No, eventually it would stop, right? Because of friction. So something that could be analogous to this is if I had like a little RC car, like a little remote control car, and I was pushing the hockey puck and I was traveling at a constant speed, right? So I'm traveling at a constant speed like this. This is my little RC car. This is the hockey puck. And then all of a sudden, I stop the little remote control car. And then the puck is going to continue on. So in the hockey puck situation, what happens to the hockey puck after I stop the car? It continues on, right? But does it go on forever? No. It eventually slows down and then stops, right? Because friction is opposing that motion. Friction is applying a force in the opposite direction of the motion. So it starts to slow it down. It starts to decelerate it, right? That's the exact same thing that's going to happen here. So I paused it just as I took off my, so the RC car is now stopped, but then the hockey puck's going to continue on, but friction is still there. So when I hit play, watch the speed. Speed starts going down because I'm accelerating in the opposite direction. And then once I hit zero, now some of the forces is back to equaling zero. Does that make sense? Cool. Now, I don't think we've got enough time for this, but what I will do is I will set this up for us to finish up next class. So I want to know, what is the value of the coefficient of static friction in this particular situation? Okay. So I want to find mu sub k, or sorry, mu sub s. Sorry. So I want to find mu sub s. So the information that we are given, we have a mass equal to what? 50 kilograms. We have an applied force, so force push, equaling 200 newtons. We have the force due to static friction, equaling a negative 200 newtons. And that should be it. Well, actually, we can do this right now. So this is actually going to be a little bit easier than I expected. So these are the knowns that we've got. And of course, acceleration due to gravity. It's going to be 10 meters per second squared. All right, so this is all the information that's given. Cool. Now, when we're writing down our knowns, we may not have to use all of them. Cool. But sometimes we might. Now, from before, the force due to static friction is equal to this equation. So these are my knowns. I want to find mu sub s. So mu sub s equals something. My equation is the one that I just circled up here. So the force due to friction static is equal to mu sub s times the normal force. Is everybody tracking so far? So based on this, does everybody understand like where I've gotten this? If there's any confusion, I need you guys to let me know. Okay. My objective is solve for mu sub s. I want this bad boy right there. So I need to get that by itself. What do I have to do to get mu sub s by itself? I divide both sides by f sub n. So it cancels on this side. The expression that I get is mu sub s come on, equals the force due to static. What? I always do that. Static friction over my normal force. Cool? Anybody confused about that? Okay. So going back to when we were solving problems before, I look at this and I'm like, all right, so on the left side, that should be in my find box. Yep, cool. And then on the right side, I should only have things that are in my knowns box. So force due to static friction, do I have a number for that? Yep, right there. Negative 200. Cool. Or what? Yeah, forget about the negative. We'll just deal with the magnitude. I don't want to get into too much detail about the positive and negatives. I just want to get the concept through. All right, and then normal force. Do we have a value for normal force? Ooh, we don't. Uh-oh. So I want to figure out, like, 'cause we have the force due to static friction given to us, but we don't have that. So is there an expression for the normal force that's made up of things that we do know? All right, so just as a quick review, in this situation, when I had the box on the ground, the normal force we said was the same thing as the force due to gravity, which is the opposite sign, right? So that's the same kind of deal that we've got going on right here, a box on the ground. So what we can do is we can say that the normal force is just going to be mg. And I know at this point in the lecture, I probably lost a lot of you guys. That's why I've got this streaming to YouTube right now. So you guys can go back and watch this. So we're going to switch the normal force and we're going to substitute in mass times gravity. Cool. So do we have the value for force due to static friction? Yep, that's right there. Do we have mass? Yes, we do. And do we have gravity? Or the acceleration due to gravity? Yes, we do. So since we have everything on this side, we can now plug the values in. And of course, this is not going to be exact, but this is the process that you would use. So the force due to static friction was 200 newtons. The mass was 50 kilograms. And then the acceleration due to gravity was 10 meters per second squared. So this is going to be 200 divided by 500. So it's going to be 2/5 or 0.4. So 200 divided by 500. And that reduces to 0.4, right? Yeah, 0.4. So that's mu static. Cool? Any questions? I know that was a lot. And I want you guys to make sure that if you don't understand something, that you contact me. Okay? So where does everybody stand? Like, give me 1 through 10 in the chat. Yeah, definitely more practice, but like, does the overall concepts, was anything just outright you did not understand? Like, just completely mind blown at any point today? Okay. Now, again, this is the first time you guys are seeing this, so I'm I if you so is having no friction similar to no gravity? So, um, the effects will be kind of similar, um, because if you don't have gravity, then you won't have a normal force pushing up, and if you don't have the normal force, then there's not going to be friction. So, in a sense, it would be, I guess so, in a very strange way. If it makes any sense, like no gravity in the manner of not floating in the air, but as in things just gliding across each other. If that's clear. Like things wouldn't be able to grip onto each other. So it would be as if I'm floating on the ground, so to speak. So they need each other. So friction is. I don't know if I want to say this. Friction is dependent on gravity. So, because the statement I was getting ready to make was friction is dependent on gravity, but my gut's telling me that that's not correct. So I'm trying to think of other situations where there is no gravity, but there is friction. Um, I mean, air resistance, you don't really need gravity for air resistance, I don't think. But air resistance is a type of friction. Um, I don't know. It's an interesting question. What I am confident in saying is, um, if objects are sliding across or sliding against each other, uh, it depends on the gravity. If that makes sense. I just saw Caesar pop in. It's all right. You get how to do the problems, you just don't really know how to set them up. Okay, yeah, no, that's fine. As long as the concept made sense, um, that's all I'm asking for today. I'm just this is the first introduction to friction. Okay, I'm not expecting you. If you guys understood this and could do problems, I would be extremely impressed. So my expectations of you guys understanding this after today, I'm not expecting that. Okay, it's okay if you don't understand it 100%, or if it's making you feel uneasy. That's okay. As long as the concepts made sense, this kind of stuff, if that made sense, but this doesn't, that's where I want you to be. Okay? If this doesn't make sense and this doesn't make sense, then we might have to, then I want you to talk to me. Okay? Everybody cool? So is there friction in space? Yes, there is. So let me modify that. So if it's in a complete vacuum, devoid or void of any um, particles, okay, then there would not be friction. But in actual space, there is stuff there, even though it's microscopic. There are things coming in and hitting all, like, you get what I'm saying? Like if I had a space shuttle, I have to design the space shuttle to withstand friction in space because there are things in space that will impact the spaceship. It could be dust from an asteroid impact that's been flown off into space, and like those microparticles are hitting it, so that does cause friction. But the term space itself, like the you know what I mean, like the best thing to do is a space that technically isn't a real thing. But what I'm assuming that's what you're referring to, then no, there is no friction in space. I know that's a very convoluted and backwards way to say it, but hopefully that answered your question. Okie dokie. I'm going to go ahead and end the live stream.